challenges we see. Mentor Graphics has been serving the aerospace business for over 30 years, and we're permitted to see best practices around the world. This is an era that's very important both in China and in the adoption of electrical design automation to the aircraft industry. If we look at the situation in particular here in China, it's a remarkable market opportunity for all of us. China has now become the second largest national air traffic market by passengers. 5 years ago, Beijing was the 14th largest airport in the world. Today, it's the number 2 by total traffic. By 2014, it's estimated that 30% of all passengers in the world will be in China, and that the growth rate between now and then will be greater than 15% per year. And over the next 20 years, we expect there will be a delivery of about 4,000 new aircraft just in China alone. And there is an enormous investment in infrastructure in progress in China, with an investment of 1.5 trillion yuan, and over 1/4 of that on airport infrastructure, on new airports, on construction of and expansion of existing airports, 56 new ones, 16 airport relocations, and about 91 renovation projects. It will be an enormous change here in China. Now, aerospace is not new to China, and aerospace cooperation with multinational corporations in other countries is not new either. For over 40 years, Boeing has worked with Chinese partners dating back to 1972 in supplying parts and working together on aircraft. Now, though, we have designs originating in China, and we have significant amounts of local production. The ARJ21 now is said to have orders well over 200, and the A320 has been in construction and assembly here in China for some time. Regional jets, a very important market for aerospace, are less important in China than in many parts of the world because you have so many people. And so air service typically requires larger jets. Smaller jets are less efficient if you have the passengers to fill bigger planes. But even so, nearly 15% of the demand for regional jets will be here in China. And China enjoys some other advantages that cannot be matched by any country in the world. If you look at cost advantage and contribution to market access, China is the optimum country in the world to focus on aerospace. And of course, this is one reason that Mentor, along with Aconsis, has built a large infrastructure to help work with the leaders in the China market. For cost, while China is not the lowest cost place to produce aircraft, it's very competitive with those that are. But the access to the local market is the most important in the world, and the combination of the two makes China very, very important. Now, there are economic benefits to China and to the world from having a healthy aerospace industry. 86,000 employees work in the aerospace industry in over 31 countries. It creates jobs, it creates economic growth, it creates opportunity. And China's record in space and military is also distinguished. The most predictable and reliable satellite launch capability in the world exists here in China. The first female astronaut to be launched into space, ambitious goals for the future, and increasing investment on the defense side leads to many opportunities for our companies and for suppliers to the aerospace industry. So there are many key building blocks for a successful industry, and they're in place now in China. This is truly the land of opportunity for aerospace. You have a national priority. We have investment by government, by business. We have a proven core engineering capability, a supply chain, a local manufacturing base, and a proven capability to integrate and build the most successful aircraft in the world. So what are the trends and challenges that we should look at and compare what leaders around the world are doing? After all, the electrical aspects of aircraft are a relatively new evolution. If we go back to the first aircrafts, this is the Wright brothers in the early 1900s, the electrical system consisted only of the electrical spark generation for the internal combustion engine with no other electrical capabilities. But today, the role of the electrical system has expanded dramatically. It's vastly more sophisticated. It provides a range of capabilities. It allows for dynamic engine control, efficiency, supports everything from night vision systems to comfort in commercial aircraft. It makes possible the protection of the environment, the minimization of fuel consumption, and a variety of other capabilities. And the complexity continues to grow. It grows every year in terms of requirements, but also the complexity of the supply chain to build aircrafts continue to increase. And as we read with every new generation of major commercial jet, and in many cases military ones, the electrical systems frequently are the limiting element for successful release to production. The trend worldwide is to what we refer to as the more electric airplane. It has to take advantage of emerging technologies in power generation and distribution, in power electronics, in energy storage. And there is a rapidly increasing amount of electrical content in every airplane, just as there is in every automobile. Reasons particularly include the ability to reduce the weight of aircraft, to reduce the total cost, to improve the reliability and maintainability, and to provide more functionality, more features, and to do this in an environmentally responsible way. And as a result, aircraft today have become network computing platforms. They have as complex electronics as the computer systems we deal with elsewhere in the world. Thousands of line replaceable units in a commercial or military aircraft. The electronic networks include a variety of both deterministic and non-deterministic networks, both electrical and optical interconnect. The cable harness interconnect involves dozens of systems, miles of wire, and every airplane is unique in its wiring, a totally different configuration than every other airplane. High on the list of issues, however, is the huge increase in the number of electronic sensors and the risks that are introduced for electronic interference. And in the same vein, the complexity of embedded software makes it more difficult to verify functionality and creates problems that are difficult to detect during the design phases of development. So it's a demanding world. We all have the pressure of a more complex set of requirements, hundreds of systems, multi-disciplines, mechanical, electrical, but we also have the pressure of always reducing cost and dealing with a very complex supply chain of different companies that must come together to produce an aircraft. And added to that, on a worldwide basis, legislation dictating safety and liability requirements, environmental requirements, and they come from many different countries, and yet if an aircraft is to fly on a worldwide basis, we need to comprehend all of the unique requirements that come through that legislation. One of the most recent and important sets of legislation comes from the EWIS, or the Electrical Wiring Interconnection System requirements, basically governing the entire wiring interconnect system and the methodology with which it's designed and implemented. DO 254 has been around for some time, but originally developed just for hardware in field programmable gate arrays. Now it's a methodology for design assurance to assure that requirements are implemented properly and tested properly and can be traced throughout the design. And DO 178, guidelines for the production of software for airborne systems, one of the most complex qualifications for embedded software, and one that is growing in complexity at a rapid rate. For the EWIS compliance, the focus for commercial aircraft is on primarily on the OEMs who are responsible for the implementation and test. But what suppliers do in contributing to it can help or hinder that certification process. And this isn't just a concern for commercial aircraft. This also shows up in military aircraft, and it puts additional pressure on companies so that the design processes will be repeatable and so that there can be a consistent strategy toward wiring. The IP, or intellectual property. Let's see. There we go. Oops. The intellectual property that is required in designing an aircraft comes from many, many different sources. Some of it must be protected, some of it must be isolated, some classified, some non-classified. And that whole data management issue is a challenge for all companies that have to integrate that information into the final design. So a new approach to design flow has been needed. And Mentor embarked on implementation of automated flows beginning in 1992. But it really wasn't until about 2000, 2002 that full capability was introduced to automate the process. While it's still possible to design a complex aircraft and have a drawing-based system, it's become totally impractical. So virtually none of the leading manufacturers in the world still depend upon manually created drawings. They couldn't meet the complex regulatory requirements. They couldn't guard against all of the constraints that are required to assure that things like electromagnetic interference is not a problem. And they would end up with problems far worse than we've heard about, and yet both the 787 and the Airbus were plagued by wiring problems that came from a lack of complete automation because combinations of drawing-based systems were used with automated systems. For the future and for the leaders, wiring has to be an automated process, and it has to be based on data, not on drawings. So let's look at the design process. So designs mature starting from a description of requirements, which is refined through the process. We decompose requirements into features, features into functions, create a logical design, a platform, and physically implement it, and ultimately generate components. Those components frequently are developed by other parties. And then, of course, we have to validate and verify the whole thing. It's the traditional V diagram we become used to, where the design starts at a high level and is refined with additional information, and then ultimately we verify it, validate it, so that when we release the product, it meets those requirements and can be tested accordingly. And each of the subsystems follows its own V of development so that it can fit into the process as a component and be integrated subsequently. Technology has emerged in recent years to automate this process, to make it implementable and make it reliable. The V has huge implications for cost and for quality. If you can compress the V, you can get to market sooner. But much more importantly, if you can compress the V, you can test more alternatives. You can make last-minute changes and have them implemented and reliable. So not only do you get to market faster, you get a more optimized design. And so competition in the world today is focused on ways of reducing the length of the time for the V process. Well, squeezing that process really comes down to three basic approaches. One is to create data flow within and between each domain to increase transparency and allow for reuse. This is referred to as the digital continuity. That is, data flows from a high-level representation to the more detailed representation. It's machine readable, it's not subject to misinterpretation, it can be used by members of the supply chain, and because it's in machine form, it can be repurposed for whatever type of design and verification is required. The second thing in compressing the V is to improve productivity by making the design correct by construction using synthesis. And this really has been adopted by the leaders only within the last 10 years. But today, I hardly visit a company that doesn't have some form of automatic synthesis, synthesis of the wiring itself, or synthesis of other pieces of the design that's done automatically, electronically, and correct by construction. And third, making the design flow manufacturing aware, so that when the design is released, there are not manufacturing problems. The constraints of the design have been comprehended during the design process, so that the release time is a time to go to production and to have everything work together. Many companies have implemented the full automation and experienced incredible results in reducing the V time. And in addition, the benefits are compounded by making clear to suppliers in the supply chain the requirements they must meet, the timetables, and to have them deal with the digital data in an automated form rather than through written specifications and drawings. So today, for most of your companies, there is at least some degree of automation associated with a data management system that covers the whole product life cycle, that utilizes what's referred to as a services-oriented architecture for passing data among the pieces of the design, so that the physical implementation of the wiring can comprehend the physical design of the mechanical system, so that the wire bundle can fit through the hole in the frame and be predictable and verifiable, and so that all of that plays together in a single data management system. Until recently, one of the most frequent complaints we used to hear is that our engineers, instead of doing engineering, spend 80% of their time re-entering and validating the data required. This shouldn't use any of the engineer's time, because the data can be automated and repurposed for each transition that occurs in a design. Bombardier has principles that they provide for their design team, and the principle one is that we must have a data-centric approach that focuses on a set of master data that is reusable for all target components and works cross-functionally between the different functions of the organization and the different functions within each part of the design. That data centricity is a key element of being a world-class manufacturer of aerospace products. So what about process improvements? What's going on in the world to make design more efficient? Well, the traditional problems of design have been the isolation of data and information in various groups. So the embedded software developers frequently proceed upon their own path, and data is not easily available to others working on different parts of the system. And similarly, the sharing of data between hardware, software, subsystem, and the supply chain is not readily available, and in many cases not kept up to date, because they don't have a full data-centric design. They don't have the ability to update the data instantaneously across the enterprise. About 2/3 of all major aerospace projects are completed behind schedule, and a substantial percentage as much as 2 to 3 years behind schedule, and so there is a lot of room for improvement. One of the big improvements in progress in most companies today is the move toward model-driven development. For model-driven development, which is a proven methodology in many areas of technology, but also among leaders in the aerospace industry is to provide a flow of data so that the requirements can be used to synthesize the functional model to which we add data, and then synthesize a structural model to which we add data and optimize, ultimately physically synthesizing the final physical model and the associated manufacturing infrastructure. Well, each of these models needs to be verifiable and executable. And so examples of this case have existed for many years. The electronics industry, for example, designs integrated circuits this way. It's not unusual for an integrated circuit with 10 billion transistors to work first time. How do they do that? Well, they do it by assuring data continuity. They start with requirements and they automatically transfer that data, synthesize it so that it will be correct by construction, and then add to it, optimize, and simulate at a high level. The higher the level of abstraction, the more rapid the simulation, the more you can verify. At each level, detail is added, but it's added to be consistent with the prior level, so that with the constraints in place, the release to manufacturing rarely has any violations that can't be met. Well, the same has been done to a large extent in subsystems, printed circuit boards, but the most exciting that's come into place really in the last 10 years is the complete flow for electrical wiring. So today, a wire harness can be defined in terms of requirements and connection points, and then automatically generated, synthesized, within the constraints chosen by the company. If your company has special policies, they can be implemented in the constraints. If you want to simulate for electrical problems, sneak paths, you can do it at an early level of the design. And the same data is used to subsequently generate the bill of materials, the factory form boards, and ultimately the final design, implementation, and the database to maintain and service the aircraft at later times. With that data continuity, an enormous part of the design problem has been removed, and leading companies today have found they can greatly accelerate their processes and move them much more quickly through design alternatives to choose an optimum design. A more challenging one is the embedded software, and it truly is not as far along as the automated generation of the electrical wiring, but it too is progressing so that embedded software can be automatically generated from a high-level description, MATLAB, UML, and verified step by step so that the final system integration requires minimum effort. Now, one other part that arises is the issue of what about simulation that occurs across domains. Things that have to be verified not just in the electrical domain, but an entire system that includes mechanical aspects, algorithmic, control systems, communication systems, and embedded software all working together. Well, this in fact has been addressed by multi-physics simulators available today from many suppliers, including Mentor. So we have customers all over the world who verify complex aerospace systems through multi-physics simulation. They take models, in this case, a landing gear that was being changed from a hydraulic landing gear to an electrical one, designing the system, generating the finite element analysis for solving partial differential equations, and using that data to build a set of ordinary differential equations to simulate the mechanical, the electrical, the control, and of course the embedded software working together. As one customer said, it's like a crystal ball that lets you see into your design and avoids enormous costs of building and testing a physical prototype. We saw that same kind of savings with a major customer building military aircraft, where they were building a system with projectiles where the actual physical tests required about $1 million per test. It's very difficult to optimize a design if it costs $1 million to test each variant. And yet by moving to a complete multi-physics simulation, in this case, a mechanical design with an electrical generator, energy storage, and a guidance system on the projectile, all of which could be optimized and tested virtually on the computer, led to an optimum design for a small fraction of the cost and the ability to test many more alternatives. Now, another element of the automation of the electrical design of an aircraft system is the fact that you can see the impact of alternative decisions. So today, leading aerospace manufacturers have the ability to take the functional connectivity model they have and automatically generate the wiring configuration under a set of constraints. They then have the ability to change the constraints, to vary parameters, and to see the effect upon weight, on cost, on other features, and thereby optimize the total design. Well, for the average engineer who works in a design, his or her piece of the design is much too far removed from the platform to fully comprehend its effect on the total system. And yet today, with the automated systems provided, you can look at different alternatives. In this case, one shown in red, one in blue, and you look at the effect you are having on the design. If you make a design decision, how does it affect the weight of the entire platform, the cost of the platform, the length of wire in the platform? All of these can be automated, can be analyzed, and can be optimized. And that is truly the way aircraft should be designed, can be designed, and will be designed in the future. And lastly, by working on a data-driven model rather than a drawing-driven model for design, the work spent on one aircraft or by one person becomes reusable, can be repurposed, and so when the wiring approach is chosen as an optimum, then automatically the manufacturing flow can be generated, the form boards for the shop floor, the technical publications, the maintenance manuals, all of the bill of materials, costing, everything becomes an automated process, and the V is greatly shortened, the optimization is far better, and the aircraft we build are more reliable, more capable of fulfilling their mission. So to summarize, increasing electrical content coupled with legislation and the supply chain challenges are causing a lot of process changes in the way leaders design and develop and manufacture aircraft. Modern integration technologies will in fact facilitate the interoperability of what have seemed to be very separate and disparate systems. The new technologies that allow us to synthesize the connection data into actual wiring to test constraints and to optimize a design is here today and widely used among aircraft manufacturers. And improving the V blend blends powerful new capabilities with the ability to configuration manage the diversity of wiring designs that must be completed in order to serve a large customer base. Shaghai.